Welcome back to the lectures on plastic analysis. In the previous lectures, we saw how the process of plastic hinge formation takes place. It's not a single point, but it is spread over a finite region. And we also saw some of the practical real-life examples of plastic hinges, like this one in the case of a fiber-reinforced bamboo composite structure. So now today we will see some of the Codal provisions regarding the plastic hinge and the type of sections which should be used in design, and also we will begin computing the ultimate collapse load and see how the approach can be extended to bigger and larger structures. So first of all, we just bring here some of the provisions of IS 800 2007 with regard to the classification of sections. So IS 800, it has clearly specified that in order to avoid the possibility of premature failure by buckling before even reaching the plastic moment capacity, the section should be sufficiently adequate enough, and this can be ascertained by limiting the width to thickness ratio of the element. So this has to be ensured, and accordingly we will see in the next slide how classification happens. The code further says that if we are using plastic analysis, then members, they should be very much capable of forming plastic hinges. This formation of plastic hinges is not enough. Rather, the section should have sufficient rotation capacity also. That is, it should have high ductility, and this should be achieved without any sign of buckling, so that the plastic hinge serves as a proper hinge. It undergoes large amount of rotation, so that when the next hinge is being formed, till that point this hinge remains in operation. It does not undergo any kind of rupture. So this is very important because the hinges, they form in a particular sequence, and it's necessary that each hinge has sufficient capacity for rotation so that it transfers the load to the adjoining regions, and in this way all the hinges, they are formed one by one, and the failure mechanism occurs at the end. So it should not happen that a particular hinge, the section undergoes rupture prior to the development of the proper failure mechanism of the structure. On the other hand, if we are using elastic analysis, then the member should be capable of developing the yield stress at the extreme fibers, either both the extremes, compression and tension in the case of doubly symmetric section, or one of them in the case of a monosymmetric section. So all this should happen without any sign of buckling. So whether we are using elastic analysis or plastic analysis, the section should not undergo any premature failure. So accordingly, the sections are classified in this category. The first is the plastic section. So these are the cross sections which can develop plastic hinges, and they also have the high rotation capacity required for the failure of the structure by formation of plastic mechanism. So typically we have seen that at point number 5 we have the stress diagram such that the entire section is in the plastic zone, but the plastic sections, they can go beyond this. A plastic section should go sufficiently far beyond point number 5. So at point number 5 the full plastification occurs. The section should be such that the curvature at the final rupture is at least 6 to 10 times the curvature at point number 5. So this is a typical behavior of a plastic section. Next, compact sections are those cross sections which can develop plastic moment of resistance. That is, they can reach point number 5, but they have inadequate plastic hinge rotation capacity for formation of plastic mechanism due to local buckling. So they can reach the full plastic zone of the entire section, that is, entire section is under the yield stress, but they don't have sufficient rotation capacity so that they can go beyond the achievement of the stage of the plastic moment, so they prematurely fail due to local buckling. Then we have the semi-compact sections. So these are the cross sections in which the extreme fiber in compression can reach the yield stress but cannot develop the plastic moment of resistance due to local buckling. So typically these sections, they can reach somewhere like this, that at one of the two extremes the yield stress in compression is reached and the other one may not have reached the yield stress, so the section cannot go further. So this is semi-compact section. And finally there is slender section. So these are the cross sections in which elements buckle locally even before reaching the yield stress, that is, they are undergoing failure even before we reach point number 2. So point number 2 corresponds to the semi-compact sections, and these, the slender sections, they fail prematurely, say at point number 1 itself. So here this table of IS 800 2007, this is table number 2. It provides the limiting width to thickness ratio for the sections to be classified as class 1 or class 2 or class 3, that is plastic, compact and semi-compact respectively. Now let's see some of the essential requirements also. So the code says that when we are using plastic method of analysis, the following conditions must be satisfied. So there should be sufficient ductility of the structure and plastic rotation capacity should also be there. So the first requirement is that the yield stress of the grade of steel used shall not exceed 450 megapascal. So there is a limit over here because when the high strength steel is used, the high strength steel lacks ductility, it's slightly brittle in nature. So that's why the yield stress is limited to 450 megapascal. Then next, the requirement is that the stress strain diagram shall have a plateau at the yield stress extending for at least 6 times the yield strain. So this is necessary to ensure there is sufficient ductility, that is, beyond the yield point the stress strain curve should extend at least 6 times. So the ratio of the tensile strength to the yield stress specified for the grade of steel used shall not be less than 1.2. Although in the analysis we are ignoring the strain hardening region, but here it's clearly specified that the strain hardening region should be there and the ultimate stress should be at least 20% higher than the yield stress. Then after this, the members used shall be of hot rolled or fabricated using hot rolled plates and sections. So cold formed sections are not allowed here. So usually for cold formed sections which are used in the pre-engineered structures, the working stress method is recommended. Then the cross sections of the members not containing plastic hinges should be at least that of compact section. So we should make sure that all the members, they are plastic, and if we should make sure that if the plastic hinge is not occurring within a particular member, it should be at least compact. That is, it should be able to attain the plastic moment capacity. However, if the plastic hinge is also occurring in the member, then the section should be plastic section. That is, it should have sufficient rotation capacity also, so that it can sustain large rotations and the moments are transferred to the adjoining regions and it does not undergo any kind of premature failure by buckling. So if, However, we are using the elastic approach, then the member should be at least semi-compact. Then the cross section should be symmetrical about its axis, normal to the axis of the plastic hinge rotation. This assumption we have already considered, that we are considering either monosymmetric or bisymmetric sections. That is, the plane of the loading and the plane of rotation, they should be same. Otherwise, there will be other effects which are not accounted for. Now let's see an example. Here we have a simply supported beam, and this beam is, say, a monosymmetric section, a rectangular section for example, and this is under a UDL. So we are increasing the intensity of the UDL in a very gradual manner. Now this is a determinate structure, so till the failure the bending moment diagram will remain same. So bending moment diagram is parabolic in nature, and let's say we assume that the maximum bending moment is less than the yield moment. And then what we do, we increase the loads further. So we increase the load such that the yield moment is exceeded, but the maximum moment, it is less than the plastic moment. So there won't be any change in the shape of the bending moment diagram till the plastic moment is reached. So now this is the condition that the bending moment has exceeded the yield moment but is less than the plastic moment. And let's say we increase the bending moment further by increasing the applied UDL, and now the bending moment at the midpoint, it just touches the plastic moment capacity. Now if the load is increased further, what will happen is that the bending moment cannot increase beyond MP, and the point B will be converted into a plastic hinge. So this is the limit to the bending moment. So the moment when we are reaching the plastic moment, at that point plastic hinge will be formed, and immediately, because the structure is determinate, the structure is converted into a mechanism. So this is the ultimate load. So at this particular point, when the load is the ultimate load denoted by symbol WU, we have the bending moment given by WL square by 8 equal to MP, and we can compute the plastic moment capacity of the section, because we have already derived that this is nothing but the product of the plastic section modulus and the yield stress. So we have the value of the right hand side. So based on this, we can obtain what is the ultimate load or the ultimate failure load the particular beam can carry. You can just repeat the analysis by considering a point load in place of the UDL for the same structure. Let us consider another example, an indeterminate structure, a propped cantilever. So for this particular structure, the degree of static indeterminacy is 1. So that means it would need the development of 2 plastic hinges for the complete collapse to happen. So we are increasing the loads gradually. So at the beginning, the applied point load is less than the ultimate load. The deflection pattern will be like this. So there will be a point of inflection somewhere here, so which marks the change of the moment from the hogging on the left side to the sagging one on the right hand side. So we can now determine what will be the bending moments. Now the question arises is that where the plastic hinge, the first plastic hinge will form. Will it form at point A or will it form at point B? So for that we just analyze the structure. We can make use of simple approach to find out the moments. This is the case of one end roller and the other end fixed. So we may not remember the exact bending moments for this case. However, we remember the bending moments for the symmetric case, which is the point load acting at the midpoint of fixed beam. So here the end moments are PL by 8. So we can make use of this result to derive the values of the bending moments for our case. All we have to do is we consider a system propped cantilever, and here what we do, we apply equal and opposite of this moment at the roller end. So there will be a carryover moment, and now if we superimpose these two systems, we get the results for our case. So this is elastic analysis, so we are assuming that right now the applied load is much lower than the load which causes the yielding. So what we find is that the bending moment at the left end is 3 PL by 16, and once we have this result, we can obtain the reactions. Because of the moment, the reaction will be different from P by 2. There will be push and pull. So one side we have the push effect, other side the pull effect, and we can then also obtain the bending moment at the midpoint. And when we draw the final bending moment diagram, this is the result. So what we find is that at the midpoint the bending moment is 5 by 32 PL, and at the left end it's 3 PL by 16, which is equivalent to 6 PL by 32. So now this tells us that when we are increasing the loads gradually, the first hinge will form at the left support. So that is point A. So collapse will not occur, because now what happens is that the structure has a degree of indeterminacy 1. So the occurrence of the first hinge only makes it a determinate structure. It needs one more hinge for the failure mechanism to form. So let's find out the particular load value at which the first hinge occurs. So this can be obtained very easily, because at this point, when the load is equal to PH1, which is the denotation for the load causing the first hinge, the bending moment at A is equal to MP. So that means we have the hinge occurring here, and we have the point reaching the full moment capacity equal to the plastic moment capacity. So all we have to do is we equate 3 PL by 16 equal to MP, and by solving this we get the load which causes the first hinge to occur. Now the structure has not failed, it can carry further load. However, there will be a difference now in the way we are analyzing. Now for the first phase, when the load was less than PH1, the bending moments, they were increasing at both A and B. When plastic hinge has formed at A, the bending moment will not increase beyond MP at A. So because of this reason, for the incremental applied load, the structure would behave like this. So this is the structure for the incremental load, delta P. So basically this behaves like a hinge and a roller system. So for the incremental load, we analyze like this. So the bending moment diagram for the incremental load will be a simple triangular type with symmetry at the mid. So the bending moment at the midpoint will be delta P L by 4 for the incremental load. So when we are increasing the load further, and then it reaches the ultimate load. So let's say at the ultimate load, the second hinge will be formed, and this hinge will be formed at B. So let's say that the incremental load corresponding to this condition is delta P U. So now the net bending moment at B will be 5 by 6 MP, which was the bending moment for the case of the first hinge formation at A, and then we have the incremental bending moment due to the incremental load. So that means that at point B, it has already reached 5/6 of its plastic moment capacity when the first hinge was formed. So it can only resist a further moment equal to 1/6 of MP. So once this is achieved, then a second hinge H2 will be formed and the structure becomes a mechanism. So what we are doing is that we are considering this structure just at the verge of collapse, that is when the load applied is just marginally less than the ultimate load. Otherwise, once the mechanism has been formed, the analysis will not be valid. So that means that the total bending moment at this point due to the first structure and the second structure with the incremental load, that should be equal to the plastic moment capacity MP. So by solving this, we get the value of the incremental load equal to 2/3 of MP by L. Hence the total load, which will be equal to the sum of the two, comes out to be 6 MP by L. So now we can just see the difference between determinate structure and the indeterminate structure. The first structure was our determinate structure. So this was the bending moment diagram. So what we find is till the yield point, the bending moment diagram is linear. So once the yield point is reached, after that the bending moment diagram starts forming a curve, and finally at the reaching of the ultimate load versus deflection curve becomes a straight line parallel to the displacement axis. But before the development of the first yield point, it's linear in nature. Now in the case of the indeterminate structures, for example the structure we just saw, the prompt cantilever, we find that the region before the yield point is bilinear. This happens because before the development of the first plastic hinge, the structure had a different configuration. It was a prompt cantilever, but for the incremental analysis it is a simply supported beam with less stiffness. So it is bilinear in nature, and once the yield point is reached, then the curve is not a straight line, but it starts getting bent, and finally at the ultimate load the deflection is infinite, so we have a straight line. So this will be the final bending moment diagram when the structure is just at the verge of collapse. So at both points A and B, the bending moments are MP. So you can find out the reactions at the final collapse by yourself. Now let's try to extend this concept to multi-span indeterminate beam, and this is under this kind of loading. So here we have the main, so we have shown here all the spans, they are under point load, and the point loads, they are related by the factors M1, M2, M3 and M4. Let's increase the load P in a very gradual manner. So this structure has a degree of static indeterminacy equal to 3. That means for the mechanism to form, 4 hinges are required. But right now we have no idea where the hinges will be formed. So for that purpose, when we are increasing the load P gradually, and let's assume that the structure is in the elastic range, so the bending moment diagram will be like this. So the first hinge will be formed at the location where bending moment is maximum. For that purpose we have to analyze the structure. Now it is an indeterminate structure. If we are analyzing it by using the forced method, we have to solve 3 equations, and then only we will be able to obtain the final bending moment diagram like this. So let's say the bending moment is maximum here. So if the bending moment is maximum here, so the first hinge will be formed here, and let's say we can now find out this load by equating the bending moment here with the plastic moment capacity of the section, which we can determine once the cross section of the section is known and the value of the yield stress is known to us. So we can determine it. Then for the incremental load, our bending moment diagram will be like this, because here at point B the plastic hinge has formed. So this is the bending moment diagram for the incremental load. Now where will be the next hinge form? The next hinge will form where now the total bending moment equal to the superposition of these two diagrams is maximum. Let's say that the bending moment is maximum now at point C. So let's say the second hinge is formed at point C. So all we have to do is we have to just equate the sum of the bending moment for the incremental case and for the original case at this point equal to MP, and this will give us the value of the incremental load for the formation of the second hinge. And after this, when we increase the load further, then we already have two plastic hinges. So for the further incremental load, the bending moment diagram will be like this. So at the locations of these two hinges H1 and H2, the bending moment further will not increase. Now the next hinge will be the location where the net bending moment diagram from the superposition of these three cases is maximum. And let's say that the bending moment is maximum at point D, and here the next hinge H3 occurs. So that means the sum of the ordinates of the bending moment for the first case, second case and the third case at this point is maximum. So what will happen is that we can sum up all these and equate this equal to the plastic moment, and this will give us the third incremental load. And the final incremental load level, because three hinges have already formed, just one more hinge will convert the structure into mechanism. Let's say the next hinge is formed at the midpoint of DE, that is under the load in the span DE. So that means the sum of these moments for the four bending moment diagrams at the midpoint of DE, that is this bending moment plus this bending moment plus this bending moment plus this bending moment, their sum should be equal to MP. So once the fourth hinge is formed, then the structure has been converted into a mechanism. It will not be able to carry further load. But this is a very tedious process, because in the first case, when we have to determine PH1, we have to analyze a structure with a degree of indeterminacy equal to 3. And for the second incremental load, the structure has undergone now change. It has a degree of indeterminacy equal to 2. And for the next case, it has degree of indeterminacy equal to 1. And for the final case, it is a determinate structure. But for each incremental stage, we have to analyze a totally different structure now. So it's a very tedious process. So here we also get to know how the sequence of the hinge formation is occurring, which is the first hinge, which is the second hinge, which is the third hinge, and which is the fourth hinge. But this is a bit laborious process, and often we are not interested in the sequence of the hinge formation. We are more interested in the ultimate collapse load. So for that purpose, we need to make the solution process faster and expedient. For that purpose, there are two methods. One is the equilibrium approach and the other is the virtual work approach. And in the next class, we'll study these methods. So thank you very much. Please join the MS Team channel of our course for further discussion and for clearing any doubts.